Section 7.3 is another method, and we're going back to things revolving again. Things are moving around, and this one's going to be called shell method. And a lot of people think that shell method is their favorite one, but I think a lot of the reason it's their favorite one is because it tends to be one that we understand best after we understand disk method and washer method. So biggest difference with shell method is now instead of making disks, we're going to create these little cylinders. And the best example I can give you of that is that soup can that I refer back to sometimes. Let's pretend like we're going to put a label on the, so we're going to take the label off the soup can. If I open up that label, what am I going to have? I'm going to have a rectangle. Oh, look, I've got this rectangle. Well, what would happen if you put 80 labels on that soup can? What would happen to the soup can? Well, it would start to get thicker. It would start to add more mass, more volume to that soup can. So what we're going to do is we're now going to go back to finding volumes of solids of revolution, but this time what we're going to do is we're going to start putting rectangles in differently. So the big difference right here, the rectangle is parallel to axis of revolution. So here's what I mean. If I look real quick, if I'm revolving this picture, this vertical axis of revolution, if I'm revolving this thing around the y-axis, normally we would have started putting our axis in, or we would have put our rectangle in this way, and that would have been, oh, there's a gap, that would have been a washer method, which is okay. And that's still going to be okay. But here's what we're going to do this time. This time, instead of putting it in that way, we're going to put a rectangle in that's parallel to the axis I revolve it around. So when I see this vertical axis like this, I'm going to automatically know that this is going to be an integral that will have a dx with it. When I look at the horizontal one, now I'm revolving it around, let's say, for example, the x-axis. Now when I put my rectangle in, I'm going to put it in this way, and that's going to tell me that this is going to be a dy integral that I'm going to be working my way through. Now, how does all this work? Well, the key to all of this is when I start looking at my volume, this cylinder that I have written up here, if I want to find the volume of this cylinder, volume of a cylinder, what would I do? I'd have to take 2 pi, I'd have to multiply by its radius, I'd have to multiply by its height, and then the thing that would be tricky, and this is where I try to use the example of the label on the soup can. If you had 1 label, it would effectively have no effect. If you had 20 labels, it would have some effect. If you had 1,000 labels, it would have a big effect. So the last thing I need to include in this thing is, what do I have going on here, is the thickness of the shell. So this thing is going to be called a shell, this little cylinder that I'm making. And basically what's going to happen is 2 pi is going to be a constant that's along for the ride. The radius is going to be the distance that goes from the center of it to, well, what's going to happen is it's going to be, the radius is going to be the, from the axis to the rectangle. That's going to be your radius. The height of it is going to be how long is the rectangle. That's going to be our height. So this is going to be, the height is going to be the length of the rectangle. And the thickness of this thing, which is going to be kind of nice, is ultimately going to end up being how fat does this thing become? How fat is your rectangle that we have going on? So your thickness is how fat's that thing going to be. And this is going to be the width of the rectangle. The width of your rectangle. Okay, so how does that translate? Well, the thing that's going to be nice is the width of the rectangle is going to ultimately end up being your dy or your dx. That's just how it works out. Because that's how you know, if you look at the difference in the 2 yellow things that I put on this picture, one is a lot thicker than the other one is. Well, that would make a big difference if you're talking about a or talking about labels on a soup can. And that was the thickness of the label. Well, it would add a lot more mass on the right than it does on the left because of how I drew it. So when we do this shell method, we're automatically going to have a new constant, and that constant's going to have a 2 pi in front of it. we're going to integrate from our lower x value to our upper x value, or our lower y value to our upper y value, depending on the variable we're using. And we're then going to multiply it by a radius. And that radius, well, what's the radius going to be on this cylinder if the cylinder, well, this would be my radius. And that radius is going to be the distance from my yellow rectangle over to the axis I'm revolving around. And I'm just going to call that for right now r of x, because I want that radius in terms of x. And over here, the radius is going to be that distance, so I'm going to call that the radius in terms of y, or r of y. And then we're going to multiply that by how long the rectangle is. Well, the length of the rectangle, I guess I shouldn't use green so we can see it, but the length of the rectangle would then be the length of the rectangle in terms of x. So that is going to have something to do with your f of x. And if I look at the length on this one, that's going to be some kind of an f of y. So shell method is the one that people generally like the most. I will tell you that there are going to be times I'm going to set problems up where you're going to have to be able to recognize and do the one that's best, and there are going to be other problems where I'm going to say, here you go, set up a rectangle to do shell, set up a rectangle to do disk, set up a rectangle to do washer, whichever one fits the best. So here we go. So number one, shell method. To find the volume of the solid generated by revolving the area enclosed by this thing. So I'm going to give you a quick sketch of what this graph looks like, and you can put it in your calculator to verify for me. But here's what your graph kind of looks like. So it kind of comes through, looks something like that. So this is going to be what our graph looks like. So this is x minus x cubed. That's your f of x. Okay, and we're supposed to be figuring this out in the interval between 0 and 1, which happens to be, coincidentally, the places that this thing hits the x-axis, and I'm going to give you that. If you had a calculator, you could certainly figure out those x-intercepts. And we're going to revolve this thing this time about the y-axis. So we're going this way. So I've got this region enclosed by that blue graph in the x-axis, and we're revolving it around the y-axis. So normally what we would do is we'd come right in and we'd draw a horizontal rectangle. But this time we're going to use shell method. We're going to draw a rectangle that way. And we're going to take that rectangle and we're going to revolve it around that axis I have labeled with the pink arrow. Now if I go to do this, we're talking about shell, and it says we're supposed to be talking about shell. So I'm going to set up my template for shell. 2 pi integral from I don't know where to I don't know where. Actually, I do know where. It's supposed to go from 0 to 1. I need enough of those yellow rectangles to get from x equals 0 to x equals 1. I'm integrating with respect to x. All I need to know is what's my radius and what's the length. So the radius would be the distance from this rectangle over to the x-axis. Well, that rectangle over to the x-axis, is it always the same? No, that rectangle could have been put in any of those spots. It's not an f of y. It's got to all be in terms of x, but it's not going to be the same. It's going to be varying. It's got to be a variable. Well, what variable represents horizontal distance if you're talking about a graph? Horizontal distance, we'll normally talk about, well, wait a minute. If you want to know how far over to go to get to that dot right there, I'd tell you that's the x-coordinate. Well, that x-coordinate might be in many different spots, but it's just got to be on that blue graph. So your radius in this case is the distance from the y-axis over to that rectangle, but it has to vary. It has to have a variable in it. That distance is going to be x. How long is that yellow rectangle? Well, this would be the length. How long is it? Well, it's not the same. It varies. It depends on what x value you use. You're going to take that x value and you're going to plug it into that blue function. So the length of that rectangle is that blue function. Just like that, I've got the shell method set up. I don't have to square anything. I don't have to do anything crazy like that. All I need to know is how far over should I go to make the rectangle, how tall is the rectangle going to be, and it's going to be based on f of x, and integrate that from 0 to 1 and multiply your value by 2 pi. Pardon me. And if I do the exact same thing with this number 2, so now number 2, this is going to be another one that we're probably going to need to draw a graph for. It looks like this is going to be kind of in the way. But here's what my graph looks like this time. So this graph kind of comes swooping down like this. And we're supposed to be dealing with this thing going from 0 to 1. So my region this time is kind of this thing right here. So this time we've got x equals e to the negative y squared. And I gave you that graph because you'd have to solve it for y in order to get it in terms of x. Well, this time we're going to revolve it around the x-axis. So normally I would be trying to set this thing up and looks like it'd be a disk method, and I'd probably need 2 different integrals, but that's going to be a problem. So this time we put our rectangle in parallel to the axis we're revolving it around, which tells us we're going to be using y's in our integral. And it looks like we're going to be, if we put it in parallel, we're going to be using shells. So we're going to start with 2 pi. All I need is a radius, and I need to know how long that yellow rectangle is. And I need enough of those rectangles to get from 0 to 1. What's my radius? My radius is the distance from this yellow rectangle down to the x-axis. What's that distance? Is it always the same? No, it depends on the y value you're using. And how long is that rectangle? The length of that rectangle, it's not always the same. It depends on the curve, which means that would be the distance from your function over to the x-axis, and it has to be in terms of y's, so that's going to be your f of y. If you plug either of those 2 integrals into your calculator, you're going to end up finding the volume of your solid revolution. So that one is kind of your third of the triumvirate of being able to find volumes of solids of revolution.